Okay, cool. Yeah, take it over.
This meeting is being recorded. Got it. Yes, so I think it was Kuhn who asked me, I don't know who came up with it, that I should come and give another talk about combinators in the memory of David Turner, who died unexpectedly like a month ago or something like that. And since he was very influential when it came to compiling with combinators. So, okay, this doesn't work. How do I get, oh, there. So there was this language called Haskell, St. Andrews static language. Static does not refer to piping, but that it was static binding rather than dynamic binding, like many Lisps had. And David Turner worked on this, and he made a new implementation of it using combinators. And there was a paper in Software Practice and Experience in 1979, I think. And so when I started my PhD here, there was a course on denotational semantics by Søren Holmström. And as some exercises in writing denotational semantics, we wrote some little Haskell code snippets. Before this, the only thing I'd heard about functional programming was that it was programming where you couldn't assign to variables. This made absolutely no sense to me. I mean, what are variables for if not assigning to them? So I thought it sounded very weird, but then writing some little Haskell or Haskell snippets, I thought it was fascinating. And then I read this paper that David Turner had written, and I thought it was absolutely beautiful. And then in the fall of 1981, there was a meeting, lots of functional programmers at Aspenäs in Lerum, and David Turner was there. So I'm sure he gave a talk. I have no memory of this. The only thing I remember was that we were walking around there, and Thomas Jonsson asked him, so do you think it would be a good idea to not just have a fixed set of combinators, but sort of make combinators for your program? One for each function, something like that. And David Turner, yeah, that sounds like a good idea. And that was the start of the G machine. So if it hadn't been for David Turner, I'm not sure I would have been doing functional programming. I might have been doing something completely different. And then combinators totally fell out of fashion. So for a while, people tried to make hardware for it. There were micro-programmed SK combinator machines, and Burroughs, which was a big computer company at the time. They had David Turner as a consultant in Texas, and they were working on making sort of a real computer that was going to execute combinators. There was a little bit of a functional programming upswing in sort of early 80s, because the Japanese had a project called the 5th Generation Computer Project. And if the Japanese did something, then everyone had to do something similar. And they were using Prolog. And so the Europeans thought, well, we have to be a little different. So we'll do something else, maybe functional programming. It was big in the UK. And it was pretty big here in Sweden too. Well, I mean, by Sweden, I mean just boy. So anyway, yes, it fell out of fashion, probably largely because of the stuff that Thomas and I did on compiling to machine code, because it was much faster. And so who needed these combinators? But now machines are much faster, so we can use the slow combinators again. It's amazing. So when I gave this talk, I don't know, 4 or 5 months, 3 or 4 months ago, I wrote a little bit of Haskell code to produce combinators. And then when I started doing that, I thought, this works fairly well. So I kept writing, and it turned into a Haskell compiler. Naturally, yes. So here's the paper I was referring to, a new implementation technique for applicative languages. And you can see the Haskell code on the left and the corresponding Haskell code on the right. And you can see that these languages back from the 70s, they were not that different from the Haskell. Well, I mean, Haskell is an old language now. What is it? Over 30 years old. Only conditionals look a little bit different in these two. So, I thought I'd give a little demo before continuing. So I'm cloning the GitHub repo for my compiler. So we have the source code now, and then we go there, and then we have to build the compiler. There, it's done. Now we can run this. So let's look at some, there's an example program here. Typical Haskell program. And you can say, got the binary in MHS. You can, oops. No, can't have a file name. It has to be a module name. Okay, binaries in EX. It works. You don't have to produce binaries. You can just run the program if you want to. Or if you don't give it any arguments, you get into an interact. Oh no, I gave it an argument. There. 1 + 2. Well, I mean, it's Haskell. As you saw, it took a little bit, took a while to load up. So this, if you don't do anything, it compiles everything from source every time. So the whole prelude and everything. But you can speed things up a little bit. You can pre-compile the prelude if you want to. Prelude. So now it starts quicker. Yes. So as a little one more thing to compile here, the compiler can of course compile itself. It would be a poor implementation of a programming language if it couldn't compile itself. The source code is in source and it's called MicroHs.main. And let's give it some flags here so we can get some runtime statistics. Yes, this is not as fast as we'd like, is it? So, I mean, this is running combinators and it compiled, I don't know, a few thousand lines, 5,000 lines of Haskell, something like that. So not too bad, but so let me remove the cached prelude and do this again. So it compiles every single line of code needed. And you can see how long that takes because I have a point later on about that. By the way, if you have any questions, please interrupt me. So that took 12 seconds to recompile everything from scratch.
So maybe I'll come to that, but
what is it? Is it compiling two combinators and then you have a runtime that runs?
Yes. So let me remove the compiler, and we can see what the.
Sorry, so the microphone will pick
Oh,
up you. So
okay.
If you can repeat
The question was, what is it compiling to? Is it compiling to combinators? And the answer is yes. So the output can be either purely textual. I think it looks like this.
Nice.
It's a description of the graph that should be in memory. Well, it's first the version of this format, and then it's the number of definitions it contains. It's 1623, and then
the compiler.
Yes, this was it. So in out.com, if you don't say anything, you get the combinators in a file called out.com, and that was the last thing I compiled. So this is the compiler. This is the combinators for the compiler.
Oh, isn't there a file there?
There might be. I mean, I know there is. So it's 280K and in this textual format. And then when you download this from GitHub, you get the runtime system, which is written in C. And you also get the version of this file, but something that is easier for a C compiler to chew on. So instead of having one enormous string, it's a byte array. This contains exactly the same string as the one you just saw. It's just as an array of bytes instead.
And this is compiled into the C program.
Let me remove. No, you can see it. It's a few lines up there. Where's the C compilation? There. So it compiles the runtime together with this file that comes with the distribution. So you just compile those two together and you get whatever it was that those combinators contain, and you get an executable that you can run. Any other?
This generated MHS.c, that's the C file which contains a string of the combinator.
Yeah, it contains exactly this stuff. But I fear that most C compilers can't handle a string that is 280K characters long, but they can handle long arrays being initialized. So that's why it's an array. I could have had characters in the array instead of decimal numbers, but
why not just have a small thing in C who reads the combinators?
Oh, yes, it can do that. I mean, if you don't, but then you don't get the binary then that contains everything. I wanted to be able to make standalone binaries. So the runtime system can read exactly those files. So if you just say, so the runtime system compiled on its own without any combinator, hasn't it made that? Okay. If you don't say anything, it will read the file out.com and run that. And so that was the last thing I compiled was the compiler. So it started up the compiler again. Okay, any more questions?
Wait, it ran the compiler and the compiler in it loaded all these files. Right?
Yeah, yes. When it says loaded, it means it compiled that file.
How big is the runtime system?
In the source or the binary?
Source, the C code.
It's about 2,500 lines. It has a bunch of stuff in it that you don't necessarily want, but so I mean, it has the combinator interpreter, memory management, and then it has a bunch of file IO things and being able to read the combinator file, being able to write the combinator file. And it just adds up, yeah.
I noticed that there's a whole bunch of combinators that were a bit unusual there. How many do you have?
I'll come back to that. I have a slide.
Okay.
I think it's 15.
One more.
Okay, then we'll go back here. So does the world need another Haskell compiler? I don't care. Yeah.
My second question, actually, the parser,
Yeah.
is it the full Haskell? You parse?
Yes. I mean, I've been a bit lazy, so it's the thing that if you try this, that you're guaranteed to run into is that I don't parse prefix negation the way Haskell should. That's pure laziness on my part. Otherwise, it's yeah. Yes, I mean, I'm partly retired, so I'm just doing this to have something to do. So I don't care if it. So GHC has a lot of dependencies and a lot of stuff. So the runtime system that I have, you can opt in or out of certain things. You can opt out of having standard IO, for instance, and you can't do any file things. But if you just want to run something on a little microcontroller or something like that, you don't want standard IO. You just want to be able to fiddle with some bits or whatever. On the other hand, if you want to try and use any packages that exist out there, they're all made for GHC, it seems. Few of them are written in Haskell. They're written in GHC Haskell. So I had one goal. And as you can see, it took 12 seconds to recompile itself. So I have failed at my goal. But
Machine theory.
this is an MacBook with an M1 chip. There is an M3 now. I would do the 10 seconds with time to spare. I can implement some more features.
So comparison, how much time does it take for GHC to recompile?
Itself, you mean?
Yeah.
I don't know, half an hour? Something like that. I haven't bootstrapped GHC in a long time. But
1 hour plus. Okay.
But GHC can recompile my compiler in 0.7 seconds. So so why GHC itself needs that much time to recompile itself, I don't know. I mean, if you want to be safe and have the compiler you produced, should have that recompile itself again, and then you should take that one and recompile itself again. I should tell you, I think I told this story last time I was talk about combinators, but I'll tell you again. Someone might have missed it. So when we did our lazy ML compiler, there were no source code control systems, and there was not much disk space, so there was no room to have many copies of things. So I made some change to the compiler, recompiled itself, replaced the binary, and then I tried it. Oops. It didn't work. There's something wrong with the new compiler, but it's the only one I have. So I have to go in with the binary debugger and fix the bug in the machine code so that I got the compiler that could recompile itself. And after that, we had some procedure with the makefile, made sure that there are always 3 copies of the binaries available 3 generations back, and you make sure that the compiler can recompile itself and produce exactly the same as the previous one, because I don't want to do that again.
So Lennart, was that the reason for the shortage of comments as well? The shortage of disk space, right? I remember, as far as I remember, the LML compiler had only one comment, and it was, "The ice is thin here, but it works."
Well, it's good that you're here. Now I can make fun of you. Oh, yes, I wanted to update this figure, but okay, so there are no surprises really here. I mean, you Lexan parse the thing. It's all written in Haskell with parsing combinators. Type check, you can see where the heavy beast is. It has more lines of code than all of the rest. put together. Desugar, and you get some lambda term, and then you do the bracket abstraction to combinators, and then you can write that out as a text file. So there should really be, sorry about people who are online, there should be an extra box in this figure saying that the output of the bracket abstraction can also go into a compilation cache, because while you're compiling, if you happen to import the same file more than once into different modules, you don't want to recompile it over and over again. So every time you have compiled a module, you stick it in a cache, and then when you start, you check if you already have the module compiled, and then you use that instead. And then when you're done with all the files that make up your program, you just take all the modules in your cache and you link them together. I mean, link, you just concatenate the files. Yes, and then the runtime system is 2,500 lines of C roughly. Yes, so as usual, it's an extended subset. So there are some missing things, but I've also implemented some of the popular extensions like rank n types and multi-parameter type classes and kind signatures and blah, blah, blah. There's no syntax for GADTs at the moment, but you can do it because it has all the machinery. You just have to write a little more to get the same thing. I've not implemented functional dependencies yet. So that's the next thing. But we can do a bunch of stuff. Something missing that I will probably do soon is to have some kind of IO refs and IO arrays, because sometimes you need to do imperative things.
I'm a bit surprised here that there is no. Why doesn't this already exist? Like a parser for Haskell written in Haskell and a type checker written in Haskell and so on.
Bits and pieces exist, but as I wanted the compiler to be able to compile itself as soon as possible, I had to write everything myself in the subset of the language that the compiler currently accepted. So it started out being really impoverished Haskell. There was no functions with pattern matching. There was only case. There were no complex patterns. There were only simple patterns, and there were not this and not that. And then as I added features, I sort of rewrote bits of the code. Also, I like to have done everything myself. I mean, can't trust it if you haven't done it yourself. So the only piece of code in there that I didn't do was the stuff that Robert did to add floating point arithmetic to the compiler. So some bits in the compiler and some bits in the runtime system. The compiler bits look very different now, by the way, because now it has overloaded literals the way Haskell has. So it's an actual parsed as rational numbers and you from rational numbers. Yeah, so if anyone happens to use this and have some feature requests, you can send them to me. If it looks fun, I might add it. If it looks boring, you can add it. Error messages, by the way, are not good. I mean, I think it says here, yes, bad error messages, boring, because, I mean, error messages, who cares? Because I always compile with GHC to get the errors. And a bunch of things that should be errors are not, you don't get any error message. Things that doesn't really matter, like you import a module and you say hiding foo. Now, there's no foo in that module. Who cares? I mean, that might be an error, but it's useful to have because it makes it more compatible with GHC. If I need to hide something in the GHC, I mean, the GHC can compile this too, of course, but it has a lot of stuff and some of it you might not want. So I can say hiding when you import some particular module, and GHC sees the hiding and hides those things. my compiler sees the hiding and sort of, nah, there's nothing like that here, so I don't care.
And can I ask about the type checker?
Yes.
I'm assuming you probably didn't use the idea of generate constraints and then solve them separately. The GHC uses, or do you? I mean, I would love to have a sort of small scale demonstration of that technique.
I do actually.
You do? Oh, great.
Well, so I use unification, and then if unification fails, it adds that thing as a constraint, and then it tries to solve the constraints at the end.
Okay, great. So that's super, because that's the trick to making GADTs work.
And the sort of the base version of the type checker is exactly from the paper that you and others wrote about how to do rank n polymorphism.
Right, but that did not have the generate constraints and solve.
No, that did not have any kind of
the outside-in paper. Yes.
Yeah.
So that's great, because that would be maybe, because GHC is very, very intimidating to, if you want to say, let's see generate and solve later as an in action, looking at GHC is not going to help you, right? Looking at your compiler might.
Yes, I mean, it's shorter, but it has no comment.
It wouldn't be by Lennart if it had comments. Thanks.
Yeah, so here's a couple of slides copied from last time I was here. So there are many combinator systems, and you can do things with very few, like only S and K, but you get enormous programs if you do that. So you want to have a few more combinators. So let me, I'll skip over what graph reduction does. I don't know if this is readable. So here are the combinators I have. Let's count them. 15, yes, I was right. And so you can see here, the ones marked with the star out here, they were in David Turner's paper about how to compile. So most of these combinators are not new. I mean, I'm sure none of them are new. Here's the Haskell equivalent of some of these combinators. So the K combinator is cool. It's both the const function, it's also false, it's also the empty list. So I added a few, like a combinator for true, that seems reasonable to have. Pair, cons. So there are two interesting characteristics of these combinators. So the ones marked with an A here are the ones that allocate the new cell. The ones marked with a star are ones that introduce indirection nodes. So when you do combinator reduction and you find something like the identity combinator applied to X, that's supposed to be X. And the application node should be updated with the result. So you could imagine, I just copy X over the application node, but you can't do that because then X might not be reduced. So then you will have two copies of X and you will do that work twice. So instead you introduce an indirection node, which I write as a little star here that says, okay, I'm pointing to the real thing. And the indirection nodes are just a nuisance that you have to always follow those. So as you're reducing, you have to see, okay, so the indirection now, well, then I need to follow it. And then when you garbage collection, you squeeze out all the indirection nodes so that they're not there anymore. So they're a little bit annoying. Yep.
Do you do path optimization while you evaluate?
No. I don't know if that pays or not. Something that would be easy to try.
Extra administration to keep track of.
There you have to do writes to memory then, or as you're going down the indirection chain. I don't know if that's. I have no intuition for what modern machines are good at. I spent at least a day rewriting the evaluator to do one push and pop less for each time you enter the evaluator. And I thought this will save something, some memory traffic. It made absolutely no difference. It was disappointing. A few combinators are nice. They neither allocate nor introduce indirections. They just sort of rearrange things and overwrite. So you might wonder, where do these come from? Well, you produce the combinator file, and I have a little program that goes through it and looks for combinations of combinators that are common. And I thought, these two occur together a lot. Let me make a new combinator for that. And I did that a couple of times. You could do something more systematic. So Oleg Kiselyov has a paper about combinators. He has a new abstraction algorithm that is better, and also he suggests a family of combinators. So it's not a bounded number of combinators, but you can implement a bounded number and then do something else when you exceed the bound. They might be better. I did a quick experiment and it didn't make much of a difference, so I kept the ones I have. I mean, in the memory of David, if nothing else.
Is your compiler parameterized by which combinators you use?
Parameterized.
I mean, can you easily change it in one place and then the compiler?
You update the code in one place and in another place and in a third place.
Because I mean, it's not only the combinators, it's also how do you decide how to compile into these combinators?
Yes, no, there's nothing elegant there.
Okay. I have another question.
Yeah.
So I saw in your code you generated, for example, lots of long strings of B, of B, of B, of B, of B, of B, of B.
Yeah.
You could try to reduce that?
That's exactly what Oleg's family of combinators. There's some, you could say B12, which means that's like having 12 B's in a row like that. Yeah, I mean, there are many things you could do here that might improve things. They might also make very little difference.
Yeah,
And you can only find out by trying. So when I change the compiler, introduce some new things, I keep a close eye on how long it takes to compile and how big the output file is. So the thing that takes 12 seconds now, it took about 6 seconds to recompile itself before I introduced all the overloading nonsense in the type checker. Because overloading hits you 3 times. Well, it's more code to compile now. And the code is now overloaded. So that it's also slower. And then what's the third one? Well, there are multiple ways that this sort of affects how things run. But I figured the doubling of the compilation time was worth it for having overloading. Because if you don't have overloading, it's not really Haskell. In addition to sort of just the combinators, there are, of course, all these things that you need that you can't do, like seek. Yeah.
How do you do recursion?
So the recursion is done in 2 different ways. If it's the top level thing, it's done by just having a name for that thing and a label. I'll show you what it looks like. If it's local recursion, it's done with the Y combinator. And if it's mutual recursion, you have to tuple them up and then take them apart.
Question here.
Yeah.
You added combinators when you saw.
Yeah.
You try to remove combinators that are not used anymore, that are useless.
They're all used. So no, I haven't tried removing. I mean, there might be one of the primed ones is not very common. It might be worth removing. Yeah.
The abstraction, the bracket abstraction, is it greedy? Try to match the largest first?
It's very ad hoc. That's another nice thing about Oleg Kiselyov's. He has written a little paper about this. He has a very disciplined abstraction algorithm, but it first switches to De Bruyne notation, which is, I mean, never makes me happy when I have to read the output. I mean, yeah. So primitives for arithmetic. IO is just another type constructor, and there's return IO, bind IO, then IO. They are just implemented as things in the runtime. So the compiler doesn't really know anything about I/O. There's no cleverness here about passing around state tokens or anything like that. They're just implemented in as operations. There's also some things for FFI, so you can call C functions. You need to have some malloc and free and things like that, so you can get memory for C. So I'm going to show you a couple of cool things about combinators. Start with self-optimization. So what does David say? The second principal advantage of the combinatory code turns out to have some remarkable self-optimizing properties, including that constant calculations are automatically moved outside loops and that the overhead cost of calling user-defined functions falls to 0 after the first occasion of its use. So here is a super simple example. So if you have f of x equals 2 plus 3 plus x, and you just compile it naively, and so here's the combinator version. If plus turns into int add, and it was int add, and then int add 2, 3. So the first time you use this function, this int add 2, 3, it will reduce to 5, and it will forever be 5. There's no need for the compiler to try to do any clever constant folding, because the first time you execute it, that constant folding will happen, and it will forever be like that. So how is this beneficial? I mean, that looked like a bit of a artificial example, maybe. So let's look at how overloading is implemented. This is the standard dictionary translation that Wadler and Blott first described. So if you have a class like num with a couple of methods, plus and from integer, you have an instance here for ints and a function increment that works on any number, and inc_int is just that function but with the type restriction int arrow int. So how is that transformed? So you can think of it like this. So the class turns into a data type with 2 fields, well, many fields, but 2 important here, a plus field and a from integer field. The instance declaration, it turns into a record of this num type that contains the things, the methods that you had, prim, int, add, and from integer. The increment function, well, the num context here, it just turns into an extra argument. So here's you pass in the num dictionary, and then plus is the selector function from this record. So you select the plus out of numdict, and then you select the from integer function from numdict, and then you use those. And then if you say, okay, I want this at type int arrow int, well, then when you solve your constraints, you find, yes, there is something, there is a num int thing, so I can pass in the inst num int dictionary here. So left-hand side is exactly like the right-hand side before. So what happens when you say, look at inc_int? Well, inc_int, as you can see, was inc num inst num int. And we do just an ordinary so substitution. You substitute inc with its body, you get this thing. And now there are things you can do. You can do reductions here, because inst num int, it should say, is a record that you have. So you can select the plus method from that, and you can select the from integer method from it, and you get this, and then finally you get this thing. So this, I showed you this reduction sequence using lambdas. This is not how it happens when you actually run the program, because you've translated everything to combinators. But exactly the same thing happens. So the first time you use the inc_int function, this thing will happen. This is not built into the compiler, it's built into the runtime system that will do these things. So let me show you. Demo. Okay, ink num a arrow a. Oh yeah. So maybe someday I will not force you to write the for alls. I said at some point every variable should be bound somewhere. It's good practice, but I also realized that it's annoying. Okay, here's the ink function. It works. Unfortunately, I can't show you the combinators for that function easily. Let me make the ink int function. It is int arrow int ink int is equal to ink. I can show you the combinators for the ink int function. There's a strange function called cprint that
What happens if you try to see print the ink?
see, I'll show you. You'll get to see something, but you don't get to see the actual ink function. It says ink. Okay, I don't know what this num a is. I better do some defaulting. Oh, I'll default it to integer. So what you see here is actually ink defaulted to the integer type and not ink with the dictionary as it is. So yeah.
Why
Why is that not the same as the ink int?
This is for integer.
Yeah, but why is that much larger?
The integer implementation is written in Haskell.
Oh, integer.
Integer.
Not integer. Okay.
Yeah. Yes. I wrote the integer package in Haskell. It's not very good, but you can see remnants of it, like here, 2 to the 31. It uses base 2 to the 31 for the digits of the integer. You can also see here, so here, for instance, is a label of something that is shared. So somewhere in this blob, it will say underscore and the same number. It means it's a reference to this point. So that this actually describes a graph rather than a tree. You can see a bunch of underscore things. And the numbers there, they're just sort of addresses in the heap.
I have a question.
Yeah.
You wrote cprint ink int. It first evaluated ink int.
It did first evaluate ink int, yes. So the cprint evaluates first. I can also do it not evaluating first, but you won't get what you want.
But now it's already evaluated, or
No, it redoes everything from scratch every time. So this is a lot more than you think. Because it's not done anything. It's not compiled yet. So you get the dump of the rest of the compiler needed to compile ink int, which is rather a lot.
nice.
Yes, so it's very hard to get that middle thing. I want to evaluate a little, but not all the way. So, but I mean, it is fun to at least have cprint, so you can. Yes. So why is this so weird? Let me. That is what you think. The other one is the integer 5, which is a list of big num digits. So P is a pair, O is a cons. I don't know what the rest is here. I mean, it's something. Let's import the example, and it had a factorial function in it. So cprint back.
It's recursive.
It's recursive, yes. There's a label out here and a reference to the label here. Now, if you are if you like to optimize code, and I do, you can see that this is not as good as it could be. The C combinator is the same as flip in Haskell, it just switches the arguments. And for equality, it doesn't matter which order for integer equality. And the same, well, so for integer minus, there is a function called subtract that have them in the opposite order. So this could be optimized, this could be optimized. I could add some more reduction rules in the runtime system that checks if the C combinator is applied to a single argument, that way you can flip the. I've thought of doing that, but I'm sure that will not speed things up. But, well, I'm not sure of anything, but it might not speed things up. Anyway, so the compiler contains nothing. It has one little optimization, but almost nothing to optimize overloading. I just let the runtime handle it.
So if you compile to like a very small architecture, you would like this to happen before you generate the code. Now it happens when you call the function the first time.
Yes, well, yes, and no, yes, no, yes. So,
right.
You can force, I mean, the thing that is done just before cprint runs, that is like RNF in Haskell, it computes things to normal form. You can do that on your combinator graph before you write it out.
But you don't.
I don't do that, no. Also,
it may be bigger.
It might get bigger, yes. Another thing you can do, if you just compile something, you get, the whole prelude will be included. And so you have a lot of stuff there that you don't need. That the first time you run the garbage collection, all these things that you didn't use in your program, they're eliminated. That you can do. You can give an extra flag to the runtime system saying, read in the program, run the garbage collector, and write out the combinator graph again. And then you'll get the minimized graph. And you could have something more that runs RNF on it. Mm-hmm. You have to be careful when you run RNF, though. So, the calls to the error function and things like that you don't actually want to run. So it doesn't. But or maybe you do want to run them. Depends on exactly what you're doing. Another cool thing as well, you've seen it now. It's easy to serialize things. So the structure in memory, there are only 3 things. There are application nodes, there are primitive operations, and there are values of base type like int and float and C pointers and things like that. So you can easily write something that dumps out this text format. You just have to do 2 passes. One pass to see where you have sharing, and then the second pass that actually prints out and put labels where you have sharing.
What about indirection nodes?
They are removed when you write things out because they're pointless. And then when you read things in, you just have to have a table over the shared nodes. That's why the file format, you said, it started out saying how many labels there are in the program, sort of definitions, so it can make a hash table of the right size to use during the deserialization. So you saw I did something that pre-compiled the prelude to speed things up a little bit. So to add that to the compiler was about 10 lines of code. You just run the compiler on the prelude, and I said there is this compilation cache that has all the modules that it has seen. It just serializes that compilation cache out to a file, and then when the next time you compile, it starts up and it looks, is there a saved serialized prelude? Oh, slurp, and it's in, and you go on from there. So I'm going to make that better so that it actually checks if the files are up to date and things like that, because you don't want to slurp in something that's not the latest version. So I'll have some MD5 checksums or something on all the files. So that's cool. I also like to be able to just have the secret thing and see what combinators things turns into. Here's another cool thing. So what if you just want to run the program? I don't want to produce combinators. I just want to run it. There was a -R flag to the compiler. It just runs it. Well, when you turn it into combinators, here are the things that it can be. An application node, a combinator. I have string as the name of the combinator, and say we only have integers in the program. So these are the only things there is. So this is a syntax tree, but I want the value that corresponds to this syntax tree. It's dead easy. Ignoring types. This takes an expression and produces an any, which is type that GHC has, that I also have that. Whatever. So if you ignore the gray unsafe coerces, you can see, well, if it's an integer, you get the integer. If it's a combinator, you look up the combinator. And if it's k, you get the const function. If it's I, you get the id function. If it's s, you get that. If it's plus, you get that. If it's an application, you just unsafe coerce the function part, and then you have the other part, and you just apply them. And if your program is type correct, this is perfectly safe. And this is what it does when you give it the -R flag. There's no generating some code that needs to be interpreted or anything like that. No, you have it there. It's just this little thing, just a few unsafe courses. And what's that between friends?
I knew we should never put unsafe coerce into GHC.
So I should point out, this does not work with the GHC compiled version.
Oh, really?
Yes, and I don't know
What
why.
happens?
You get the seg fault.
Oh, well, it's got unsafe coerce, isn't it?
Yes, but it's all perfectly safe, I promise.
That is mysterious. You should
So
try
it
them.
works for anything that doesn't do IO. It's only when you do IO that it crashes. So I suspect there is something special about IO, that you can't unsafe coerce to and from IO without being shot in the head.
You just need to throw in some unsafe perform IOs there too.
Yeah, I tried many things, but then I gave up and compiled it with my compiler. I would like it to work with GHC. Okay, so
Sorry,
why?
Lennart, I forgot. Did you told us that data structures are represented by their church encodings?
Yes.
Right. Right. So there's no built-in values. They're just all more functions.
Everything's normal functions. There's some base type like integers and double and so on. Everything else is just church encoded.
Yeah. Okay. Thanks.
I didn't mention this in this talk, but yes, all data types are church encoded. I've noticed that this makes me very reluctant to add another constructor to a data type, because every time you add a constructor, everything grows, because you need one more lambda bound argument for that one. And every case analysis has to take care of all the constructors all the time. So I might try with a different encoding of data types. But so far, this has worked fairly well. And it's easy. And it's also, in some ways, very clean. Yes, so why shouldn't you use combinators? Well, I already mentioned that recompiling the compiler takes 12 seconds with my compiler and 0.7 seconds with GHC. And if we do some really classic benchmark, this nfib functions, which is like fib, but it has an extra +1 at the end. The extra +1 has the cool feature that the number you get when you run nfib is exactly the number of function calls you've made. And you can see, but if you compile it with my compiler, you get, well, so I should back up. If you take the number, if you run it with some argument, take that number and you divide it by the time it took, that's the number of nfibs per second. And that sort of should remain constant, regardless of what input you give it, because it's sort of the number of function calls per second that you're capable of doing. So MicroHaskell can do about 8 million per second, and GHC does 540 million per second. So that's a substantial difference. This is doing a lot of arithmetic, and the combinator stuff is particularly bad at arithmetic. I mean, it has to thread all these arguments into all the right positions everywhere. So it's not the fastest, but then again, it recompiles itself fast enough. No, it's not fast enough, but it's tolerable. Yeah.
That case is that compiling to sort of recursive function with unboxed arguments, or is it?
It's just GHC with whatever 002 or 03 or something. You have to ask Simon what it does. I don't know. Yes, I'm sure it does unbox numbers. Yeah. This has it has a type annotation saying int on this. If it's integer, I don't dare run it with integer because my integers, as I said, they're written in Haskell. They're not particularly good. Just in the remaining 3 minutes, I'll tell you something about the runtime system. So there are two evaluators. One that just sort of it evaluates pure terms, so it does the combinator stuff, and then there's one that executes IO actions. So you should only give it an IO thing. If you give it something that's not IO, it will just error out and say this was wrong. So that's what implements sort of return and bind and so on, and all the calling FFI and things like that. Yeah, I'll skip that. I'll just show you some C code. Here are the combinators. So there are lots of macros here, of course, to make it a little better. So the S combinators checks that there are 2 cells left, checks there are 3 arguments, and then it will build some new applications, X applied to Z and Y applied to Z, and then it will overwrite the top level applied onto that thing, and there's the decoding it. And so there's a bunch more there for the primitives. And here's the one that does the IO thing. It still has to handle applications nodes. And then we get to bind. Well, it has to have 2 arguments. Then you evaluate the first argument, or not, sorry, you execute the first argument. You get the value back of executing the first argument. Then you build a new application with the second argument and whatever you got from the first one. And then you continue. And then it's almost the same, except you ignore whatever you got from the exec IO. And return just overrides top. And then there's a bunch of stuff for C calls, and there's a catch that does a set jump in C, and then you long jump when you get an error. So this thing has a bit of a problem. A lot of the time when you run programs, the binds will be very deeply nested on the left side. So the bind, bind, and the bind, and the bind. And that means that you get in here, you get this one is the first one. Okay, so it does exec IO on that, which does exec IO on that, which does exec IO on that, which does exec IO on that. So you get a deeply nested call stack. And it's easy to run out of stack, especially on Windows that has pitifully small stacks. But you can at runtime recognize this. So if you recognize this thing, so if you recognize this combination, a bind of a bind of a blah, 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 then you at runtime rewrite it. You do this transformation, which is valid for the IO monad, and it's valid for any monad, but in particular for the IO monad. And now you have sort of reassociated it and you don't get this deep recursion. That should be a similar one for them, but I was too lazy to do that, and I didn't seem to run out of stack for them. There are lots of things you can do at runtime. Memory. application nodes, 2 pointers, and 1 bit stolen in one of the pointers to indicate that this is an application node rather than something else. And if it's something else, that bit is set to 1, and then you have, say, if you have the S combinator, you have some code here, some small number for to say this is the S combinator. If it's an integer, some other code that says it's an integer, and you store the integer here. If it's a C pointer, you have some tag and then something that points to memory in C. You don't care about memory in C so much because it doesn't participate in garbage collection. So what do you do when you garbage collect? Well, you have your evaluation stacks, you run through the stack and you mark everything you find in the stack. And how do you do this marking? Well, you have a separate array of bits. So you don't do the marking in the nodes themselves. I mean, that's one way of doing it, but it's much more efficient to have a separate bit array, 1 bit per node. You just set the bit, rather you clear a bit, you set all bits and then you clear a bit if it's been used. And then there's no scan. This is a mark scan garbage collector, but there's no scan phase. Well, the scan is built into memory allocation. So when you need a new node, you look in your bit array to find the next node that has not been marked. And you can do this very efficiently. You have a pointer. I mean, you have the bit array is a bunch of words, and you have a pointer in the next word you should look at. You grab that word, and then pretty much all modern CPUs have an instruction called find first set that finds the first bit that is set in the word. So you do that, you get a bit that is set in this word, which means that that node is free, or you get some code back saying there is no free, and then you advance your pointer to the next word in memory. So that get the grid. I had the traditional one that sort of had a mark bit in the node, and this was an enormous speed up to get rid of the scan phase, because now you don't have to touch the memory that you're not using. You only touch the memory that you are using during the mark phase, and then some memory in the bit array. And then you only touch the other memory when you actually allocate it. So that was a nice speed up. Yeah.
One of the biggest problems with the fixed set combinators is the granularity is very small. So you generate an enormous amount of garbage.
Yes.
Because you build things and take it apart.
Yeah. Yeah.
What I found is that having two garbage collectors, one reference counting, also 1 bit reference counting, gives you a lot of that back. You don't have to generate that. You thought we used.
I have thought of using 1 bit reference counts. I haven't tried it.
Right.
It may or may not be worth it. As I said, my intuition for modern machines is way off.
Yeah.
It
Yeah,
might.
true.
It's. Yes, as I said, the runtime system has very few dependencies. You need malloc and free. You can have a standard IO if you want. You can have the floating point math library if you want. You can have some Unixy things if you want. It's good if your machine has find first set. I mean, you can do without it. I've tried it on Mac OS and Windows and Linux. I've not tried it on any 32-bit systems because I couldn't be bothered to bring one up. So the binaries are reasonably small. So if the hello world binary is 712 bytes, I mean, the code for hello world, not combined with the actual runtime system. If you make an executable for hello world, it's 75K. If you're low on memory, there is this cool program called UPX that works on many platforms. It takes binary and it compresses it. And in the beginning, on the startup, it has a decompressor. So it just sort of decompresses the binary into whatever it was before as you start the program. And if you run that UPX on your hello world, it shrinks to 28K. And the whole compiler compressed with UPX is 79K. So it's a bit smaller than GHC.
For your domain to do.
But have you tried UPX or GHC?
I haven't. I should. that would be fair. Also, UPX doesn't work on Mac OS. There's some, it used to work, but Apple changed something that they're not telling what they changed. So future work, whatever I feel like. And I have a very long list of things that I'd like to do. More questions?
Let's thank Gunnar. So we begin with questions in the room. How about questions online? Lennart, do you have a sense of whether your set of 15 combinators is sort of a reasonable one to keep the intermediate representation under control? I'm wondering if there's any kind of theoretical comparison with the size of lambda calculus.
Well, I mean, if you have a fixed set of combinators like that, I think you cannot avoid quadratic blow up in the worst case. But the files are small enough that it hasn't bothered me yet. I'm a very practical person, so if it's good enough, it's good enough. If you want to have a better set of combinators, you should check the paper by Oleg. And I mean, he has a family of combinators where he can prove that the size is linear, but then the number of combinators you need is basically unbounded. Well, it's bounded for any particular program, but you don't know beforehand how many combinators you need. But probably that number is small enough that it would be a practical thing to do. Now, if that is fast or not, I don't know.
Thanks.
So just to take an example. So if you compile the whole prelude and dump the compiler cache, then you can see here it's about 2 megabytes, which I think is fine. It's not excessive. Of course, it is excessive. I mean, 2 megabytes, that's enormous. The first combinator interpreter I wrote was on a 16-bit microprocessor. I think I had 32K of memory. I managed to have a little system that could compile itself for a small functional language, but that kind of filled up the whole memory. So yes, I mean, everything here is excessive. But
does that prelude.com have all the spaces in it?
yes, I mean, that's it. Let me. It's this.
Okay, yeah.
Which is a lot. It's 150K if you compress it. And actually, I have a simple compressor as part of the system. So you can compress the binary file if you want, then it will decompress when it reads the file. So it's not as good as gzip because I only do the Lempel zip. I don't do the Huffman coding of the code words.
So are you still using the recursive mark and speak in your runtime?
Yes, the mark is recursive, but it's only so when you have an application node, it recurses in one branch and jumps in the other branch. And I carefully picked which one by testing it out and see which one uses less staff in practice. So yes, I would like to do pointer reversal there.
So I sent
Maybe.
you a PR on.
Yes, I know, but that used
That uses an extra.
yeah, I can't have that. It has to fit in the 2 words that the cell size is. But there's an evaluation stack that you have on the side as you go down. You don't have to have an evaluation stack. You can use pointer reversal as you traverse down the spine as well, and avoid that whole extra stack. So if you're really short of memory, there should be a whole other thing that uses pointer reversal for the spine stack and also during garbage collection. And both of those together, that could be hairy.
But when you get garbage in the middle of evaluation. But
Yeah. Also, I mean, it would be nice maybe to add a parallel evaluator to this at some point. And I don't know what happens when if you have in the middle of some pointer reversal there. So you probably have to have a lot of atomic compare and swap instructions as you are reversing down.
But did you find a way to do it without using 2 extra bits?
No, you can. No, it's not. You need 2 bits, but there are like 7 bits that are unused. So because the all pointers are aligned on the 16-byte boundary, so there are lots of bits.
Any further questions?
Sorry, could you go back to the evaluator?
Yeah. The C code?
Yeah.
Yes.
So this is a recursive C function.
Yes.
Have you considered building your own stack and flattening it, or instead of using the C stack?
Well, yes, that's if I do the thing that I was just talking about, doing pointer reversal instead of having a pointer stack on the side, that would also entail getting rid of recursion in here and sort of encoding what state you're in the bits in the words as you are pointer reversing. So
I see. I thought that was just the pointer reversal for the
so
collect.
I didn't mention that, but I mean that I would know that as part of it. So I should have mentioned David Turner again. So David Turner made an implementation of a language called Miranda, which was sort of the precursor to Haskell. Well, if David Turner had agreed, there would not have been Haskell. We would have used Miranda, or that would have been the language that everyone uses. But he was selling Miranda systems, and he didn't want others to implement it, and he had a trademark on the name and so on. So that's why Haskell came about. His implementation, he open sourced it a while ago, so you can look at it. And I looked at it, and David carefully uses pointer reversal instead of an extra stack, and no recursion in the evaluator, but he sort of does these tricks and encode where you are using some extra bits.
You have to do well, you have to be careful with strict functions, because if you don't want a recursion in there, if you don't want to.
Yes.
You can do the trick. You have to do it.
You implement these optimizations before you know it. You start implementing the G machine, or maybe go to the SCG machine, or right.
So no, I think what I would do here is probably, if I wanted to do something that higher performance, is to have a just-in-time compiler. You have something in there that detects when you're starting, something gets hot where you're in a particular thing, and you generate machine code for whatever that combinator sequence is doing. So then you can take advantage of the self-optimizing thing before you start generating code, which means I don't have to write all those passes in the compiler. You can still have a stupid compiler and then have it shifted. But these are just sort of, no, this might be a fun thing to try. And I mean, since I'm partly retired, maybe I will.
All right, let's thank Lennart again.
Yeah.